Okay, so this is not a so we've moved from pure randomness. We have pure randomness, just stuff messing around, but it's additive, right? So there is a memory in that system, but you don't remember any of your. You just remember the accumulation of all the flips before. You don't remember this how you got there exactly. You just know that you have 43 heads and 12 tails, and it adds up. Oh, sorry, you just know that. You don't know that you have that. You just know the difference between them. That's all. So that's a really simple kind of system. It has some memory, but not too much. So this is something that's not really about a mechanism. It's just something that power laws kind of scaling can come from, or power law size distributions come from. So lots of basic distributions that we can understand, and they make complete sense for existence, right? So Gaussians, of course, exponentials, and then there's going to be simply two variables of a system connected by some scaling relationship, which again we can understand or explain very simply, right? So here's the abstract version of it. So we have some random variable x. It's got some probability distribution p, and I'll go through an example. And then we have some second random variable, and they're connected through some function, right? Basically. And this is the elaboration of how this would work out. So the probability that y has some value. You have to sum over all of the, you have to find where the x's for which function of x equals y, and then add up all their probabilities with the right dx's in there. And if you go through the whole thing, this is what it looks like. You have to worry about that too much. It's usually best to just sort of work through this on a case-by-case business and understand this is the generalization, right? So but the differential gets replaced by this piece here, and that's going to be the important thing, generally speaking. The probability of x, you just have to put in the inverse function for y in there. But it's really in that differential. Right, often easier to do by hand. So let's do an example. So we're just going to start off with, we have some power law relationship between variables. Very important thing in here is, right, so it's this inverse. We're going to look at y large, and that will be for x small. We're going to have some nice connection between them. So let's start this thing off. We need a dx and a dy connected to each other. So we have y equals this blob. So dy is d blob, right? This is y here. So we're just going to differentiate that. These are always, not complicated things. Constant is still here. Minus alpha comes down the front. Minus alpha minus 1. And then the dx, right? So that's our connection between the two things. If we're trying to replace dx, we have to bring all of this blob, or especially this blob, over to the other side and replace x with y. So we're going to do that. So our dx is going to have this form. I've brought all of this over. X to the alpha plus 1 now, right? This was x to the minus alpha minus 1. And then this has to be replaced by y, x in terms of y. And that's what this is. Right, so still the same constant at the front. X is y divided by c to the power of minus 1 over alpha. So this is x, y divided by c. And then this whole blob here. And then we've got minus 1 over alpha in there as well. So this is really where it all happens. This is where it all happens in these transformation variable things. The dx is here, the dy is here, and now we have a y to some power, some negative power. So this is a very real thing that happens a lot, but it means that we have a couple of components that we understand well, and we can get to this third piece, which is, has some interesting, potentially quite dangerous behavior. So it depends how you want to write this, but this is y to the minus 1 over minus 1 over alpha. So so you can see there's a which is good. It's good to identify that minus 1 by itself. Maybe I should do that. Really like that frog. Okay. All right. So then we got to go and do our transformation. This is the right probability distributions connected to each other. We have y equals x. We're going to assume it's a one-to-one thing. So we're going to replace x with what it is in terms of y. Right? This is this blob, and this is the piece we just worked out on the previous page. Here it all is. So for y large, this could be, and therefore x small, this could be something going towards a constant. Right? This is going towards 0. This could be going towards a constant. Everything is happening here. Right? So if this was a Gaussian distribution or an exponential distribution, as y becomes very large, this blob in here becomes small. It goes towards 0. This goes towards a constant, And everything that is interesting is in that, in the Jacobian. Sure, it could be. Okay, right. That's what this says, right? So if it goes to a non-zero constant, all the fun is there. It could scale as something itself, right? So if it scales as x to the beta as x goes to 0, then we get an extra scaling in there as well. Fine. But whatever the case, you actually really, yeah, you get out a parallel. So that's a relationship we will use again. I just want to put it out here. It's not a bad way to get there. Exponential distribution, for example, right? So this is actually plugging something in. This is the exponential here, the same connections we've had before. If you go through, then, as I said, because this tends towards zero, towards a constant, it's really all in the differential part. Exponentials come from randomness, right? So that all makes sense, and then we have to have some story for why these two things are connected. Okay, as I said, robustness, forests, all sorts of systems kind of have this story going on. Excited about that.